All right, so let's put all of this together about confidence intervals by looking at a few examples. So let's look at heart rates. Suppose we have a survey of 20 students. These students are randomly selected. And we find that the mean heart rate of this sample is 65.8 beats per minute. Suppose we know the standard deviation of the population is 7.1 beats per minute. So that's our value of sigma. That's the population standard deviation. Let's construct a 95% confidence interval from the sample for the true mean heart rate. Right? And let's interpret the result. So we're given a sample mean, which is 65.8 beats per minute, and we're given a population standard deviation of 7.1, and we know the sample size is 20. So in this case, the population is a set of all Harvard students, and we just have a random sample of 20 students from Harvard. Well, let's calculate the standard error. So the standard error is just our population standard deviation divided by the square root of our sample size. When we do that calculation, we get this standard error of about 1.588. That is the standard deviation of the sampling distribution for the sample mean, in which the sample mean is, in fact, the heart rate for students, right? And from a random sample from the population of all Harvard students. So then we can just calculate a 95% confidence interval. With a 95% confidence interval, right, we want to capture 95% of the sample means around the true population mean mu, which we don't know. So to do that, we can multiply the standard error by 1.96, both positive and negative values. And so in effect, what we do is we take our sample mean, we subtract 1.96 times our standard error, and then to find a lower bound, and to find the upper bound, we take our point estimate and we add 1.96 times the standard error. And we get this interval of 62.7 to 68.9. Now to interpret that, what we say is we're 95% confident that the true population mean heart rate, in which the population is all Harvard students, is between 62.7 and 68.9. Right? To put another way, if we were to repeatedly and randomly take samples of a size of 20 students from the population of all Harvard students, we'd expect 95% of these intervals to contain the true population mean. Now let's look at another example. Statistics actually originated in part through studies of agriculture and biology. So let's look at this example of livestock feed and marketing. Suppose a feed supply company has developed a special feed supplement to see if it will promote weight gain in livestock. So their researchers report that 77 cows, so that's a sample size, gained an average of 56 pounds, and that a 95% confidence interval for the mean weight gain for the supplement produces a margin of error of plus or minus 11 pounds. Now, margin of error is simply that value of z star times our standard error. We call that a margin of error. So the margin of error here is simply 11 pounds. That's the value of 1.96 times the standard error. So you can think of our point estimate plus or minus the margin of error. So staff in the marketing department wrote these following conclusions. And we might say, did anyone interpret the interval correctly? So let's look through this. So we know that this is one conclusion they made. 95% of the cows studied gained between 45 and 67 pounds. Okay, and again, that is just based on this point estimate of 56. All right, and so you might say, well, when you take out a point estimate plus or minus margin of error, we get this value of 45 to 67. So they might say, well, 95% of the cows studied gained between 45 and 67 pounds. Is there something wrong with this? Well, in fact, there is, because we know the weight gain of those cows who were studied. We have these 77 cows in our sample. We could just look at the data and we know what the cows gained in the study. The point is that the 95% confidence interval, it doesn't refer to this sample. It uses the sample to generalize to the population. Right? We're trying to make some claim about the population used on the sample. That's because the 95% confidence interval refers to the population mean of cows, not the average or the properties of the cows we actually studied, because we know the properties of our sample. We know the sample mean, we know the range, we know all these different values of the sample. We don't know the population, though, unless we conduct a census. So the marketers might also say, we're 95% sure that a cow fed this supplement will gain between 45 and 67 pounds. Right? Again, this is incorrect. Right? The 95% confidence interval refers to the population mean. It's a way of using our sample data to make some claim about the population mean. Right? The claim of the marketers, when they say we're 95% sure that a cow fed this supplement, they're talking about some particular cow. Right? We don't know if a particular cow fed this supplement will gain between 45 and 67 pounds. What we are 95% confident of is that the true population mean weight gain, right, is within this interval. Right? We're not sure about any particular cow. Again, let's see another interpretation. Another marketer for this company says, we're 95% sure that the average weight gain among the cows in this study was between 45 and 67 pounds. Again, this is incorrect. Right? We are 100% sure that the average weight gain of the cows in this study is 56 pounds. Right? Just look at the sample mean. We know the properties of the sample. Again, the 95% confidence interval refers to the population mean. It refers to this process of repeatedly randomly taking samples of the same size from the population and putting bounds on these different point estimates, and to the extent that we're 95% confident that the true population mean lies within a particular interval. So I just want to emphasize this, that what we mean when we say that we have a 95% confidence interval, formally what we mean is that 95% of samples of this size will produce confidence intervals that capture the true population parameter. Again, this is a bit long-winded, so often people will say we are 95% confident that the true population parameter lies in our interval. 95% confidence interval, the key point is that we know the properties of a particular sample. We're 100% sure of the average weight gain in a sample, but we don't know the population. But we do, using what we know about the sampling distribution, the properties of the sampling distribution, we can say that we're 95% confident that the true population parameter lies within our calculated interval. So a few things to know for this topic of interval estimates and confidence intervals. First of all, we have point estimates and interval estimates. A point estimate is our single best guess for some population parameter in absence of additional information. So for the population mean, mu, our single best guess, our point estimate for that population mean, mu, is simply our sample mean, x bar. An interval estimate is a way of giving a range of plausible values, because sometimes it's useful not to have just a point estimate, but sort of a range of values to make some kind of generalization from a sample to a population. So an approximate 95% confidence interval, it's given by the point estimate plus or minus 2 times the standard error. Confidence intervals can be wider or narrower, but there's a trade-off involved, meaning with a higher level of confidence, right, that value of z star is going to be larger, and your interval is going to be wider. With a lower level of confidence for a given sample size, that z star is going to be smaller, and then your interval will be smaller. The key point is that there's a trade-off involved, and the really only way around this trade-off is to have a larger sample size, because with a larger sample size, the standard error is smaller, and the standard error is a crucial part of calculating an interval estimate, because interval estimate is simply that point estimate plus or minus z star times the standard error. So with a smaller standard error, we have smaller confidence intervals. And then, of course, be careful when you interpret confidence intervals. Again, when we have a 95% confidence interval, it just tells us we're 95% confident that the true population parameter lies within that interval. Right? In fact, we know the properties of the sample, but the idea is we want to use the sample information to generalize about some unknown population parameter.